A NASA Jet Propulsion Laboratory geophysicist involved in that research noted plainly that scientists had expected increased earthquake probability, specifically on the Elsinore and San Jacinto faults following that Baja event, precisely because of how close those fault systems sit to the original earthquake's location. Interestingly, that same research found the Baja earthquake actually appeared to relieve stress on the San Andreas fault itself, slightly reducing rather than increasing the likelihood of a major quake along that specific fault line. A reminder that stress transfer between fault systems doesn't always move in the direction people might intuitively assume. The critical distinction, then, comes down almost entirely to distance. Earthquakes in Baja California, sitting just across the border from Southern California and sharing the same broader tectonic boundary system, can and have demonstrably increased stress on connected fault lines extending into the United States. Southern California Earthquake Center researchers have explained this connection in fairly direct terms, describing how, on the scale of the entire planet, the plate boundary between the Pacific Plate and the North American Plate functions essentially as one continuous zone, running from Southern California down through Baja California and beyond, even though it doesn't form a single tidy fault line, but rather a complex series of blocks sliding past each other. Friday's earthquake, however, struck near the Chiapas coast, close to the Guatemala border, thousands of miles south of that specific Baja California and Southern California connection point, operating along an entirely different section of plate boundary involving the subduction of the Cocos Plate rather than the strike-slip motion that characterizes the San Andreas system further north. In practical terms, this means Friday's quake occurred far outside the geographic range where direct stress transfer to California's fault systems would be considered scientifically plausible. None of this means Southern California's earthquake risk is anything other than genuinely serious, and it's worth being clear about that, because the reassurance regarding this specific event shouldn't be mistaken for reassurance about the region's overall seismic hazard. Just last month, in June of this year, researchers published findings indicating that the southern portion of the San Andreas Fault, along with the adjacent San Jacinto Fault, sit under their highest stress levels recorded in 1,000 years at a junction researchers have described as an earthquake gate, a critical point that could determine whether a future major quake stays contained to a single fault or cascades across both simultaneously, spreading damage from north of Los Angeles through San Bernardino, Riverside, and the Coachella Valley all at once. The lead researcher behind that study was careful to frame the message not as one demanding panic, but one demanding urgency, urging city managers and emergency planners to treat a joint rupture across both fault systems as a realistic planning scenario rather than a remote, worst-case hypothetical. Separately, geological research examining sediment cores from both the Cascadia subduction zone in the Pacific Northwest and the northern San Andreas Fault has identified evidence of synchronized earthquake activity between those two zones going back roughly 3,000 years, suggesting that a major rupture in one system has, historically, sometimes triggered a major rupture in the other, where the two zones meet near Cape Mendocino in Northern California. United States Geological Survey seismologists have separately estimated a 7% chance of a magnitude 8 earthquake striking California within the next 30 years, and have noted that Southern California specifically appears to be, in the words of one researcher, locked and loaded, with stress that has built up over time and could, once it begins releasing, continue unleashing destructive earthquakes for years once that process starts. So where does all of this leave the actual question people have been asking since Friday morning? The honest, evidence-based answer is this. Friday's magnitude, 7.3 earthquake off the coast of Chiapas, Mexico, occurring more than 2,000 miles from California's major fault systems, does not pose a meaningful direct risk of triggering a significant earthquake in California. The distance involved is simply too great for the kind of direct stress transfer mechanism that has, in past cases, genuinely elevated earthquake risk on California, faults following closer Mexican earthquakes, specifically those originating in Baja California. Some extremely minor dynamic triggering effect, in the form of imperceptible seismic nudges to already stressed fault segments, remains theoretically possible, given how far seismic waves can travel through the Earth. But researchers who study this exact phenomenon are consistent in describing such effects when they occur at this kind of distance as minor and not comparable to a genuine trigger for a major damaging earthquake. What Friday's earthquake does represent, alongside the genuine tragedy and disruption it caused for millions of people across southern Mexico, Guatemala, and El Salvador, is a vivid, immediate reminder of a hazard that California faces entirely on its own terms, driven by its own fault systems, its own accumulated centuries of tectonic stress, and its own well-documented, currently elevated risk profile, one that exists regardless of what happens along a completely separate stretch of the Pacific Ring of Fire 2,000 miles to the south. Understanding that distinction actually matters quite a bit, beyond simply satisfying curiosity about this particular news cycle. It would be genuinely reassuring, in a misleading way, to treat California's earthquake risk as something primarily driven by distant, occasional trigger events happening elsewhere in the hemisphere, because that framing implies the risk is somehow external, sporadic, tied to headline-grabbing events rather than an ever-present condition. The far less comfortable truth, according to the researchers actually studying California's fault systems directly, is that the risk sits locally, persistently, and is actively building right now, independent of what happens in Mexico, Guatemala, or anywhere else along the broader Ring of Fire. The San Andreas and San Jacinto fault junction, sitting under its highest stress levels in 1,000 years, isn't a reaction to Friday's Chiapas earthquake. It's the product of centuries of steady, ongoing tectonic pressure building directly beneath Southern California itself, a process that continues whether or not a major earthquake happens to make international headlines somewhere else in the world on any given week. For the millions of people across southern Mexico who experienced Friday's earthquake directly, the immediate concern remains assessing damage, supporting recovery, and preparing for continued aftershocks in the days and weeks ahead, a process aided somewhat by the encouraging preliminary reports of limited severe damage and no immediately confirmed fatalities as of the most recent updates. For people in California wondering whether this specific distant event changes their own personal earthquake risk in any meaningful way, the clear, research-backed answer from seismologists is no, not directly, not from this particular quake, given its considerable distance from California's fault systems and the well-established science distinguishing between minor, wave-driven dynamic triggering and the much more significant, proximity-dependent process of direct stress transfer between connected fault systems. What Friday's earthquake should prompt more usefully than anxiety about an unlikely chain reaction stretching across 2,000 miles is renewed attention to California's own independent, well-documented, and currently quite serious earthquake risk, one that exists on its own terms, driven by its own geology, and that deserves ongoing preparation, regardless of what happens anywhere else on the Ring of Fire, in any given week or month. What happens next depends entirely on which version of the story you hear, and that variation is itself part of what makes Irish folklore so enduring. In one telling, Finn crosses the water and beats Benandonner outright. In another, considerably more clever version, Finn gets his first real look at Benandonner from a distance and immediately realizes the Scottish giant is enormously larger than he is. Rather than panic, according to this version, Finn's wife, sometimes named Una, comes up with a trick. She disguises her husband as a giant baby, wrapping him up and placing him in an oversized cradle. When Benandonner arrives and sees the supposed infant, he's terrified, reasoning that if the baby is already this size, the father must be an absolute monster of a creature. Benandonner turns and flees back across the causeway toward Scotland in a panic, tearing up the crossing behind him as he goes, to make sure Finn could never follow. What's left behind, according to the legend, is exactly what you see today: the broken, jagged remains of that once complete stone bridge, still visible on both sides of the sea, since a strikingly similar formation of basalt columns exists directly across the water on the Scottish island of Staffa. There's yet another version of the tale, less commonly told today but recorded by folklorists over the years, in which Finn isn't building the causeway for battle at all, but for love, constructing the crossing so he could visit a Scottish woman he'd fallen for, only for his own grandmother to repeatedly summon storms, specifically to wreck his progress and keep him from leaving Ireland. In that telling, Finn does eventually make it across the finished causeway, but arrives so utterly exhausted from the effort that he dies in his beloved's arms shortly after. Whichever version you happen to hear locally, the underlying image stays consistent across every retelling: a massive stone crossing, deliberately destroyed, leaving behind exactly the kind of broken, jagged coastline formation that still exists at this exact location today. It's a wonderful story, and it's survived for a genuinely good reason, because, in a strange way, it isn't actually wrong about the underlying shape of what happened. The story describes a bridge violently destroyed, leaving broken fragments scattered on both sides of a channel of water, and the real geological history describes almost exactly that: a single, continuous, volcanic event that created matching basalt formations on both the Irish and Scottish coastlines, later separated by rising sea levels and millions of years of erosion. Folklore scholars actually have a specific term for this kind of story, calling it a geomyth, a traditional legend that emerges from communities trying to make sense of a genuinely real, observable geological feature using the storytelling tools available to them long before formal science existed to offer an alternative explanation. Geomyths like this one appear all over the world, wherever ancient communities lived alongside dramatic, unexplained landscape features, volcanic craters, unusual rock formations, sudden coastal changes, and needed some framework, however fantastical, for making sense of what they were looking at. The giant was never real. But the broken bridge he supposedly built really does have a twin sitting across the water in Scotland, and the real explanation connecting them turned out to be almost as dramatic as the myth itself, just measured in millions of years instead of a single afternoon of two giants trading insults across the sea. The Giant's Causeway has drawn visitors specifically to marvel at it for at least 300 years, according to historical records, long before mass tourism, long before viral marketing campaigns, long before drones or social media existed to manufacture false mysteries around it. Early visitors in the 17th and 18th centuries arrived specifically because word had spread of this strange geometric coastline, and their accounts helped establish the site's reputation as one of the natural wonders of the British Isles, well before Victorian-era tourism made it more broadly accessible. Ownership of the site eventually passed to the National Trust in 1961, and the organization has overseen a significant expansion of protected land around the immediate causeway itself in the decades since, alongside an £18.5 million investment in modern visitor facilities designed to handle the sheer volume of people now drawn to the site every year. Today, it draws well over 500,000 visitors annually from around the world, and it remains, alongside its wider surrounding coastline, the only UNESCO World Heritage Site in the whole of Northern Ireland. The surrounding cliffs, marshes, and grasslands are also home to roughly 50 recorded species of birds and more than 200 documented species of plants, adding an entire layer of genuine ecological significance to a site that's often discussed purely in terms of its dramatic rock formations. There's a fascinating scientific footnote buried in that early 18th century history that rarely gets told alongside the giant legend, and it deserves more attention than it usually gets. When the Giant's Causeway was first formally presented to the Royal Society in London in the late 1690s, the scientific community was genuinely divided over what it was even looking at. This was still an era when the fundamental processes of volcanic geology weren't yet well understood, and the columns' near-perfect geometric regularity struck many educated observers as simply too precise to be the product of natural, unguided processes. Some serious thinkers of the period speculated the columns might be an achievement of ancient human engineering, essentially a strange, forgotten piece of architecture, rather than something forces of nature had produced entirely on their own. It took decades of continued study, more careful mineral analysis, and comparison with other basalt formations discovered elsewhere in the world, before the volcanic explanation became firmly established as scientific consensus. In a strange way, the Giant's Causeway has been generating exactly this kind of debate over whether something is natural or artificial, ordinary or impossibly designed, for over 300 years now, long before modern internet mystery channels ever existed to manufacture a fake version of that same debate using CGI and a decade-old advertisement. It's worth remembering, too, just how genuinely strange this landscape looks in person, because that reality is exactly why it has always attracted this kind of mythologizing, long before viral marketing agencies or clickbait channels came along to accelerate the process. Walking out onto the columns themselves, visitors move across what looks, from certain angles, almost like an enormous honeycomb tipped onto its side and flooded by the sea. Each individual stone fitted so tightly against its neighbors that in places you genuinely cannot slide a fingernail into the seam between them. Structures nearby carry names locals have given them over centuries of storytelling. Formations like the Giant's Organ, towering vertical columns resembling the pipes of a cathedral organ, or the Giant's Boot, a single stone naturally weathered into a shape strikingly reminiscent of an oversized boot left behind on the shore. These aren't invented mysteries requiring a fake video to generate interest. They're simply what happens when ordinary people, across 3 centuries, keep encountering a landscape this visually strange and keep reaching for stories vivid enough to match it. It's also, somewhat charmingly, become the subject of an entirely different, much smaller, but very real modern-day headache for the National Trust. Visitors have spent years wedging coins into the cracks between the basalt columns as a kind of good luck ritual or personal memento, and conservation officials have had to launch active public campaigns begging people to stop, because the corroding, expanding metal is actually causing measurable physical damage to columns that have otherwise survived completely intact for 60 million years. Removing the accumulated coins safely, without further damaging the surrounding rock, has been estimated to cost more than £30,000, according to figures released by conservation staff working directly at the site. It's a strangely fitting footnote to the whole story. A landscape that withstood tectonic upheaval, millions of years of ocean erosion, and the philosophical scrutiny of some of history's greatest geologists is now being quietly chipped away, one souvenir coin at a time, by the exact tourists drawn there by its legend. So the next time that drone video resurfaces, the stone slabs swinging open, the darkness behind it, the archaeologist supposedly left speechless, remember what it actually is. A 10-year-old tourism advertisement built by a real ad agency for a real heritage organization, using real visual effects, released honestly at the time as a piece of viral marketing, and only later stripped of that honesty by people looking to borrow its shock value for their own view counts. The Giant's Causeway was never hiding a secret chamber. It's been standing in plain sight for 60 million years, in full view of anyone willing to actually walk out onto it. An entire coastline of geometry precise enough to make ancient storytellers reach for giants to explain it, and precise enough to make modern geologists spend 2 centuries working out exactly how ordinary cooling rock could ever produce something that looks this deliberately, impossibly designed. That's really the whole point worth carrying away from this one. The manufactured version of this story needs a fake door, a fake chamber, and fake government secrecy to feel worth watching. The real version needs none of that. It just needs you to actually look at what's already there. A genuine geological wonder, old enough to have watched entire continents drift apart. Mythologized by real people trying to make sense of something extraordinary long before science could explain it. And now, ironically, mythologized all over again by people who could have simply told the true story and let it speak for itself. Sometimes the real story was never buried behind a door at all. Sometimes it's just sitting out in the open, waiting for someone to actually look at it honestly.